ready. All right, great. So yeah, welcome to the second part. And I'll just give a short recap of what happened yesterday. And then we'll try to start after that. So basically, yesterday where we got is to understand both, how machine learning is formulated and how Bayesian problems are formulated and what are the differences between them. And then we try to write that, the Bayesian side as an optimization problem, and then compare it to the machine learning side. So yeah, we started with the big goal that machine learning people have about designing machines that can learn like humans. And I showed you why human learning is so amazing. And then we talked about what are the challenges in current machine learning methods, which is basically about adaptation. I'm sorry if you hear some scratch, that's my cat who is playing here. Then I showed you some failures of AI and another setting, and then talked about what we really need to fix in the system. And then I argued that because Bayesian principles explain the human side of learning, the learning of cats and dogs and living beings, our hope is that now we can use the same principle to unify machine learning algorithms, and that's kind of is the focus of this talk. So basically, we went through the first two parts. We motivated what Bayesian methods actually do, why are they useful, and we contrasted that to machine learning, usual machine learning framework where you only have one model, so one theta that you find by minimizing this kind of loss function. But Bayesian methods are trying to find not just these one models, but actually the uncertainty around that. So we motivated that by looking into this example where there was an imbalance in the data. And even if you wanted, you could not just go out there in the world and collect more data about the underlying thing that you're trying to measure. So these kind of things happen quite a lot. And then I try to say how Bayesian principles are trying to fix it by maintaining distribution over a range of models instead of just one model. But then it's not scalable because you need to integrate. So you need to do this integration that's at the bottom over really huge space, maybe billions of parameter, high dimensional integral, and that is the issue. So we saw some more ideas of why Bayesian principle could do this kind of like human-like lifelong learning. You could do this kind of updating of your beliefs using Bayes' rule, but again, the computation is infeasible. So many of these examples we went through, deep learning and their benefits, and how we are kind of now trying to bridge the gap between these two worlds that look very different. One is estimating the point estimate, and the other one is using this Bayes rule to compute integrals. And of course, there are pros and cons of these methods, but it'll turn out that if you rewrite the left-hand side in an optimization formulation, we'll see that they're actually not that different. And that is the part we are kind of going to focus on today. So how can we bring the Bayesian principles and the machine learning with this kind of point estimate based methods together? So we started with writing the Bayes rule as an optimization problem. And I hope you were convinced and you remember some of this derivation, but basically the point is that you're going to write this integral as an optimization problem. And the optimization problem is over the space of distribution now. It's not over the space of the parameter, but it's over the space of the distribution over those parameters. If it's not clear, I hope that in a few slides, this will become a little bit more clear of what I really mean by optimizing with respect to a distribution. Okay. But the important point to remember in this slide is that this is kind of like a maximum entropy principle where you're trying to fit the data. So you're trying to somehow minimize the loss over many samples taken, many models sampled from your distribution, these kind of lines, and you average them. So you want to explain the data well, but you want the entropy to be highest possible with this constraint, right? So So that is the formulation that we're going to look at, and we're going to go into the history of it a little bit, and then maybe let's start with the first modification that we need to do to bring the world together of this machine learning and the Bayesian world. So essentially here I've shown you the same objective. Second, I'll close the door. So this objective that's shown on the left is the one that is the machine learning objectives, just going to estimate just 1 point estimate. The one on the right is the Bayesian objective, but now I have made a slight modification here that you may not notice at first. But what I've done basically is that I have restricted the space where the optimization takes place to be a restricted, like some subset of that distribution, like all distributions. So let me maybe just go here and show that this was P before. So it's the space of all distribution. And now what I've done is to replace it by Q, and Q is a subset. So maybe it's the I've restricted the distribution to maybe just be Gaussian. And the space of Gaussian distribution is a subset of the space of all distribution. So this is the modification that we do, and sometimes people call it variational inference. And now we're going to solve the same problem, but just with this restricted thing. So we're going to refer to it as generalized posterior approximation. Right? So the previous one here, this over P, when you do the optimization, you come up with a Q star that is equal to the exact posterior, exact generalized posterior, because you can include any loss function, not just log probabilities. But now we are going to restrict them to a Q, a subset, and we're going to call it generalized posterior approximation. So we are approximating the solution now. Now it turns out that with this approximation, the two worlds can be almost made the same. Okay. And let me give you an example of what that approximation might look like. So you can think of this Q to be a Gaussian. In that case, it will have a mean and a variance. And what you could do is you can sort of plot this objective function with respect to the mean, which I've shown in the x-axis here, and the variance, so it's standard deviation. And you see that now the objective looks like this. So suppose the loss is something that takes this form. Okay, so it has multiple local minima, and lower is better because it's a loss function. So you probably want to get here. But if you plot that in the space of distribution, so when you're trying to optimize the mean and the variance of the distribution, instead of just optimizing the parameter theta, then your objective will be now, it'll have two dimensions, one corresponding to the mean, the other corresponding to the variance. And you can see that it takes a certain space form. What you need to understand is that if I let the standard deviation to be 0, which is this Dirac delta distribution, then the expected loss, just this term, will go back to the original loss. So that's what I'm showing you here. Standard deviation 0, then this expected loss is just the original loss. But what I could do is now I can slowly see what happens as I increase the variance. So I'm now letting this Dirac delta go a little bit wider. And when I do that, then I see that some of these local minima that appears at other places, they get, they disappear, they get smoothed, because I'm basically now sampling over many examples. Okay, so you can imagine that each curve, each point here is sort of obtained by convolving with a Gaussian that is sort of lying like this. So let me actually see if this annotate will work. So you can think of it as like a Gaussian sitting here at one point, and you're now sampling many points like this, and you're averaging over all of those points to essentially get 1 point here. So you choose the standard deviation and then you smooth. And because of this smoothing, you essentially, you disappear, like some of these local minima. So the spurious one, maybe not that important one, they get smooth if the standard deviation gets a little bit higher. So you can see why this objective has a better property, that it's somehow is robustifying the original loss function that had a lot of local minima. But now when you start to sample from a distribution and smooth and average over it, then the higher the standard deviation you have, the smoother the objective function it is. But you need to find the right standard deviation such that only this more prominent local minima remains while the other one disappears. Okay, it's a very subtle point, and I'm happy to have discussion over this in a few minutes. And please feel free to send questions, by the way. So it's okay to interrupt and ask questions. Okay, so this idea, it actually appears in many other fields, and it's kind of a very Bayesian idea, because you're trying to look for, you're searching for a global minimum, suppose. And what you can do is you can try to have the search distribution that's trying to smooth the spurious one. So you're trying to figure out what the variance should be. And over time, you kind of sample your landscape, and landscape tells you that, oh, I could go a little bit wider, or I should go a little bit narrower. So you're trying to kind of focus your attention with like a lens that blurs the loss function appropriately, right? This is really used in a lot of fields like global optimization, as I said, also online learning, reinforcement learning, where you're using policy distribution to search for, in the value function space. Okay, so there are some references that I've added here. Maybe that helps for you, but we'll return to the history of it and why this is an important idea. But let me just answer, seems there's a question here. So Aditya is asking, does this process still remove the non-convexity? So it's a very good question. So the question is, when you do smoothing, does the loss function, the resulting loss function, the Bayesian one, becomes convex? So actually, there are papers on this, and there's a method called Gaussian homotopy. If you read my summary notes, I have actually pointed to the reference that you should where you can find what Gaussian homotopy is. But there, people have done work on showing that there is a sigma, there exists a sigma, so there is a standard deviation above which the resulting objective will be convex. Okay, so you can always find a standard deviation. Of course, this holds under some condition on the loss function. But if you find that standard deviation, then the objective could be convex. So if your Q was not here, actually, if it was space of all distribution, you can prove that the objective is definitely strongly convex in the space of all distribution. But when you start to do restrictions, then this is, it's a little bit tricky, and only limited results hold. So this is an open area of research that has not been explored, in my opinion, but we don't have time, otherwise I would talk more about this. There's another question, is about, would it lead to overfitting? Well, it's quite the opposite. It will lead to, it will avoid overfitting, because you're not, you're not only looking at one point. You're sort of smoothing things. So suppose if you're here, then if you were really looking at the original loss function, it will give you, it'll overfit because it might go to this place, but actually maybe you should be here. So if you actually look at more possibility, you sample from your distribution, it helps you to kind of not be so narrow and not overfit to one solution, but rather take samples, take more opinion from different models to average. So it does quite the opposite. I hope that makes sense. There's another question. So by Igor, so in the Bayesian framework, seeing more data equals smoothing the objective function so that the minimum is easier to find. So that's a question, is that true? So unfortunately, it's saying quite the opposite. So of course, if you get more data in any world, Bayesian, non-Bayesian, you always, with more data, your objective function is kind of getting rid of these local minima. Actually, that's what is happening as you go to the limit of infinite data. Then your minima is sort of becoming more and more prominent. So that happens with everybody. So it's not just a property of the Bayes. But in the Bayesian method, even with finite data, you have this external mechanism, which is sampling in your landscape to smooth out the objective function. So that is kind of the advantage, that you could actually have collected more data, and that would help you. But in that earthquake example, for or in epidemic with coronavirus, you cannot really go out and collect the right type of data that you need. So the distribution actually gives you an external mechanism. For example, you can think of like RL. In RL, you don't always have the ability to collect the right kind of data because the robot is still kind of learning to stand up, and it cannot just suddenly run and give you more data about running. So it's better to use a policy that somehow is going to sort of search for better ways to explore the world. Right? So intuitively, you can think of that in that way. So that's the kind of advantage of being Bayesian. Another question: how do we determine the domain of the generalized posterior approximation? That's a good question that will become clear soon. So it's just going to be parameters of the distribution. So for Gaussian, it's going to be mean and variance. And we're going to go and look into exponential family approximation. Okay, so these are all good questions, and I think these might become clear in the next slide. So let's move on to the next part, and then we'll get back to these questions in a few minutes. Okay. All right. So thanks a lot for asking questions again. Let's see how much. Okay. So let's first gain a little bit more understanding of what this posterior approximation is, because that seems to be the question that many people are asking. So what we're going to do, we're going to restrict our attention to a particular form of approximation, call it exponential family approximation. And they usually take this type of form, meaning that the distribution, it has a sufficient statistics, and its log of this distribution is linear in that. So basically, if you do log of q theta, then it's going to be linear in t of theta. Sorry, there's a mistake here. This should not be a of theta. This should be a of lambda. I'm really sorry. I think there's no other dependency on theta. Theta only appears in this term. So if you don't kind of understand this form, you can think of a Gaussian. So in the Gaussian distribution, you see that it's written like this. So this S is the precision matrix. It's the inverse of the covariance, and M is the mean. And you can rearrange these terms to have one term theta and the other term theta transpose. Okay, so this is just kind of a rearrangement and ignoring the constants. And here, T of theta, the sufficient statistics is theta and theta transpose. So there's a linear part and there's a quadratic part. And the things in front, so it's the mean times the precision, and the precision divided by half, and the negative of that are now lambda. Okay, so lambda is a natural parameter, and we'll see that this parameterization will play an essential role in understanding how machine learning is related to this kind of more sophisticated Bayesian stuff, more complicated Bayesian stuff. But this form is, if you don't kind of see this point here, then just remember that lambda is the natural parameter, and you can write it in this form, and the sufficient statistics is just linear in the quadratic in the Gaussian case. Another thing that will be important is the expectation parameters, which is basically just the moments. So the expectation of theta and expectation of theta transpose. We call them moments of a Gaussian. There are two moments for a Gaussian. So to summarize these things that will be important for the next few slides is that the distribution, always think of them as maybe Gaussian. So these are exponential family approximation with mean and the precision. So the inverse of the precision is the covariance. And lambda is the expectation, is a natural parameterization such that it's linear in the sufficient statistics, right? So these two guys are just these two, there are two of them. And the expectation parameter, there are basically two of those, expectation of theta, expectation of theta transpose. Okay, so if you just remember the notation, it will be okay. So you see what we are doing now is we are going to do optimization with respect to lambda. So that will be the parameter that we'll be searching for. It's basically equivalent to say that you're searching for mean and the precision. These two things are equivalent because there's one-to-one mapping between the two. So you can also just think in that term. But an important parameterization, mu, and a relationship between lambda and mu plays an extremely important role. And so that's why I'm insisting quite a lot about the parameterization. Okay, so what is this relationship between lambda and mu that kind of makes everything, everything the same in the future? Is this duality associated with these two parameterizations. So this is actually a very old known thing but a good reference for this is Wainwright and Jordan, 2006, where they have written this thing in quite detail, and it's also easy to read. Essentially, the space of parameters. So this is kind of the subset over which you're going to search for the best mean and the variance, right? You're trying to locate your distribution at some place. You're trying to find where you should put this distribution at. And so you're going to search in the space of lambda. But for every lambda, there exists a mu, because it turns out that this parameter mapping is one-to-one. And this mapping goes through the gradient of the function that we didn't talk much about. But essentially this this should be lambda again, so sorry for the confusion. But this is something that makes sure that this distribution is normalized to 1. It's called log partition function. For Gaussian, I think you could think of these normalizers that you have in front of the Gaussian, and that's basically the A of theta. But this log partition function is something that maps between lambda and mu. Okay, that seems quite complicated, and it seems like why we learning about this thing, but turns out that this is the key to connect the two worlds. Okay, so not only that you can go from lambda to mu by taking the derivative of this function a, this is a strictly convex function, it turns out, you can also go back. So you can write something called convex conjugate, or it's like a transpose of a matrix that you can think of. So it's basically just transpose that's inverting it. And this transpose is a one-to-one operation, meaning that you can go from here to there, and then you can go back. Okay. Now, with this, it turns out that there's a very nice property that there's something that we call natural gradients in information geometry. And I'm sorry that I'm giving too many concepts now. I'll probably lose many of you, but I hope that I can, when we go into the some details, when we leave the details, you will at least remember the whole essence of what we are doing here. So an important property here is that when you compute gradients here in this space, it turns out that those gradients are now a special kind of gradients computed in this space. And these are called natural gradients. These are related to information geometry of the distribution Q, in the sense that this gradient on the left-hand side is now scaled by a Fisher information matrix. Okay, so the geometry of the distribution, and I'm not going to go into the definition of Fisher information matrix. All of these things are actually given in this paper, so you can go and read the detail. But essentially, you are rescaling the gradients on the left-hand side. That's preconditioning the gradient, making them sort of nicer and flatter. So it's somehow smoothing the gradients on this side. And it's actually quite nice that what we realize when we actually look at the Bayesian objective, that this entropy that appears in the Bayesian objective for exponential family, when you take the gradient of that in this side, in the expectation parameter space, it turns out that it's basically mapping you back through this A star lambda. So the inverse of this partition function is actually the entropy. Now, not lots of details here, but this is kind of the key why Bayesian methods are actually now be related to non-Bayesian methods. That this mapping, when we introduce this entropy in the objective function, it's kind of like giving you a mapping back to the natural parameters, okay? And the gradients that you're computing on this side are special kind of gradient that are in natural gradients. So this slide, I'm happy to discuss this more soon, but this is kind of the key to understand the relationship, this Bayesian perspective, why it's a more general perspective. It may not make sense right away. It takes some time, but hopefully we get to that when we discuss the question. So now we are ready to state the final result, to talk about why solutions of Bayesian objectives are special, why they are covering all the solutions, are many solutions that you will encounter in machine learning with loss functions. So the magic lies in the stationary point. So if you go back to, sorry, let me just go back to the Bayesian objective, the objective look like this. What is a stationary point, meaning what is the optimum of this objective looks like? You know, the optimum of this guy is basically gradient of the loss set to 0. So the optimum of this would be gradient of this objective set to 0, right? And that's basically what I have done here. I've taken the gradient of that Bayesian objective, I get the gradient of the expected loss, and I get the gradient of the entropy to match, okay? Perhaps I should write it in there. So maybe this is not clear. Let me try this out. I hope you can see my screen. I hope you can see my writing that I'm going to do now. It takes a minute to update on my iPad. All right. So can you read this? Yes, I hope you can. Can you see? Okay. So if this is readable, I'll use that size. Okay, good. So people are saying yes, so it's a good sign. So let me write this more clearly. So if you have minimum of theta of a loss of theta, the stationarity condition for this is basically at the optimum. So I have indicated the optimum with theta star. So it's the maybe the map estimate or something like that. So it minimizes theta star is equal to argument. Okay. Okay. So for Bayesian objective, we're doing basically the same. Now we're saying it's the minimum over Q of theta, and it's expectation over Q of this loss minus the entropy of Q. And now I could do the same thing. I could say, well, this argument will be some Q star of theta. Ultimately, actually, I'm going to write this thing as, because I'm parameterizing the distribution by lambda, which is the natural parameter. I'm just going to write this as lambda. So this is the natural parameter. For Gaussian, it is S times M and minus half of S. Okay. And I'm basically now minimizing over. So I'm going to remove this and I'm going to say lambda. And I'm going to write this then as with dependence on lambda. And this will also depend on lambda. And I'm essentially just now taking the derivative of this with respect to mu. So that's a important detail, that I take the gradient with respect to mu. So I will set gradient. This is equal to the gradient of the expected. Okay, so I hope that this this sort of makes sense to you, that essentially we are just matching the two gradients. Now I showed to you in the previous slide that, okay, where's my slides? Okay, so here. So I showed to you in previous part that the gradient of the entropy is essentially just lambda. So let me write this again. It turns out that the gradient of this term, gradient of the entropy, is basically lambda. So I know, sorry, I should use the star here everywhere to show that this is the optimum. So it's going to be lambda star. This is the optimum distribution, which will be equal to negative here. So if this is a little bit confusing in the end, this lambda star actually depends on mu, right? So it's I hope that you could see that the gradient with respect to mu is basically taking through lambda star. So if this makes sense to you, then we can go back and then we can look at this slide and sort of try to make sense of this a little bit more. So, so basically what I've done is I have taken the gradient of the Bayesian objective and I've set it to 0, and then I've got this equation. And this equation is essentially saying that the natural parameter is going to be equal to the gradient of the loss, right? And you can see that this solution is different from the solution that you get if you only use the machine learning technique. If you use the point estimation thing, machine learning one, it will just be the gradient of this loss set to 0. But here now you're setting the gradient to some lambda star, okay? And now this is really the fundamental equation. And now rest of the talk, we'll just try to understand this and show through example of why this is so important, okay? So I know that this has been a little bit difficult thing for you to maybe bear with me for all this time, but I hope that it'll all be worth it. Okay, so let me just quickly say this, and then we'll go to questions, and then we'll go to examples to see why these things are useful, okay? So here, there's an important point that is happening, is that you have natural parameter on this side, and you have natural gradients on the other side. What will happen is that we'll see that natural gradients are like this digging machine that will try to bring in important information from the loss. So essentially, when you choose Gaussians, then you'll see that these will start containing information about the first order derivative of the loss, second order derivative of the loss. And then these information will be assigned to the natural parameters. And the natural parameters are made of mean and the covariance. So appropriate information will be matched, okay? And this is kind of the concept. This is the principle that I'm claiming that works behind most of the learning problems, that important information are digged through a posterior approximation and then assigned to the natural parameter of the posterior approximation. And that is the way that we can see many of the machine learning techniques that a wide variety of machine learning techniques that are being used right now in machine learning, okay? And it's been very kind of difficult thing to convince people that this is a very fundamental equation. It's important has been sort of missed in at least in the Bayesian community, Bayesian machine learning community. And I've taken many years to really bring it down to one equation that I believe is the equation that unifies most of the thing. So here we are. Let me look at the questions a little bit. The goal now is that we've almost gone 35 minutes now. So the goal would be to do a simple example to understand this equation. And once we understand this a little bit better, then do another question round. And then last 1 hour, we'll do essentially understanding how this relates to SGD or Newton's method, and then see how it can compute uncertainty for deep learning. Okay. So, okay, so questions. I'm gonna go back to, sorry, I got it. Okay, so there was a question by Ishraq. How do we determine the domain of the generalized posterior approximation is using a subset Q similar to feature transformation? So I hope that the subspace Q, now it's clear to you that Q is basically the parameters of the distribution. It's the set of all parameters. So it could be the set of mean and the covariance. And I hope that that is clear now. So we are going to choose natural parameterization basically of the exponential family most of the time. Okay, Arun has a question. How is the prior p theta determined in your earlier example of classification lines? So the prior here, I have assumed that the prior sits in the loss. So this loss function that I'm showing, maybe I should escape this, just show the slides so that I can also write at the same time. So whenever I'm actually using this loss function here, I'm assuming that the prior is included there. So you can think of like, if you're doing logistic regression, then you can think of it as just like an L2 regularizer. Let me actually just write this because we need this anyway. So let's write an example of loss that will make it easier for you to understand. Okay, I'm trying to work this out. Okay, so I'm here. So we're gonna actually do the ridge regression example, and let me write the loss function for ridge regression. You may know this already that, so suppose you have, output y, let's call them y1 to yn. These are like scalar observations. And then suppose that you have features x, and these x's are x1 transpose to xn transpose. It's the feature matrix. And suppose you have theta, that's kind of for a linear model. Maybe they're p parameters. In that case, the linear regression objective can be written as this. I hope most of you know about this already. And what we can do now is that we can add a small regularizer here. So let's just use one ridge regression. So it's theta transpose theta, and maybe there's a half that's in front of everything. So I hope that you understand that this is basically the likelihood, well, log likelihood, and this is the log prior, and that's basically what I showed in my slide. Okay, so log p of theta and log p of d given theta. Okay, so I'm assuming that this is kind of included in the loss. Okay, another question here is, so it's question by Debolena, are we varying the standard and deviation to find out which Gaussian distribution minimizes the expression? This is, yeah, perfect interpretation. So this is exactly what is going on. Let me draw a picture that will make it a little bit more clear for you. So think of the loss function being something like that. You could see at the bottom. And what we are doing now is that we are essentially putting a Gaussian distribution. So suppose I choose this point. Instead of looking at the gradient just at that one point, now I'm putting a Gaussian distribution here. Okay, And then I sample from this Gaussian distribution. So I look at this value, this value, this value, all of these values, and I weigh them accordingly. So I'm basically computing the integral of the loss. Okay, let me write the finite sum part, which is kind of easier to understand, that maybe these are all samples, and I'm just looking at the value of q theta at those samples, and then I'm multiplying that by the value of the loss, right? This is really the approximation to the expectation. So you can see that if your standard deviation, okay, I hope that this is clear, but you can see that if the standard deviation was very, very small, so let's look at another point, maybe the distribution is like this, then expectation of the loss will be almost same as this value at the mean, right? So I hope that this makes it clear that the point where you want to evaluate the loss depending on the spread of the distribution, it might be more local or global, and the Bayesian method is trying to find the right kind of diversity to sample multiple. It's the jury. How diverse the jury should be, it should be just enough to explain the data well. Okay, so, okay, I think Nazal asked a question about how do we get this capital Q, and I hope that is clear now. Rishikesh has a question on, could you please explain the intuition behind how varying the variance of Q theta helps in smoothing the expectation of loss? And I hope I have done that now. So I guess if you fix the distribution to be like maybe of something like that, then maybe the objective function would look like that, because you have averaged over certain places. But if you change the distribution to be something very, very peaky, then the objective function will be exactly the same. Like that. Okay. So it's kind of like, what should be the blurriness of my lens, the Gaussian lens, so that I can get the right amount of detail. And another word, I want the right amount of diversity. There are many ways to say the same thing. Okay, that's the beauty of it. Okay. Does the fact that one space is visualized with smooth convex set and a polygon imply something important? So this is a question by Pat, and I'll repeat it. Does the fact that one space, so I think it's they're talking about, sorry, let me pull up the slides. They're talking about this picture. In this picture, the right-hand side is a polygon, and it has this kind of cornered thing, and the right-hand side is a regular shape. And they're asking if one space is visualized as a smooth convex set and the other one is not, and this is exactly right. So the expectation parameter has certain properties, like each line there is like a moment constraint, and there's some beautiful theory about it. And this is another aspect that has not been explored that we've been actually working on. So I will really encourage you to look more into Wainwright and Jordan and understand that. Okay. Okay, the last question by Zhu Yong. Sorry if I pronounce that wrong. Does the broader Q implies less inductive biases? If so, is there a metric measuring the amount of inductive bias quantitatively for the set of distribution? Does the broader Q implies less inductive bias? I don't think that is the case. So I think what is happening is that you're deciding the space of the parameter, space of the model. So there are different kind of models, and now you're sampling from those models. So somehow averaging will sample like less complex and more complex model, hopefully. And when you average over them, the average is more stable. So it's not like you're really making a decision about inductive bias of the model. But I would not say that you're wrong also completely, because the entropy will sort of favor you to go to solutions that have lower complexity. because to get less disagreement, and you can think of, maybe I could draw this picture here for you. To understand this is that suppose you're doing, you have a classification problem, something like this. Sorry, let me do this. Then if you have a more complex model, the more complex model could go like that. It could also go like that, and it could also go like, right? But simpler models are more stable. So simpler models will be more smoother, right? And so if you want to get less diversity in the solution, you tend to focus on simpler model. So in that sense, it actually helps, but it's not doing it directly. So I hope that that answers the question. Okay. Will the smoothing function always be a Gaussian distribution? No, that's not, that doesn't have to be. So yeah, but I'm saying again and again that we should think about Gaussian because it's an easier one to understand, and exponential families are in general quite complicated. All right, so this is very good questions, and I hope that one property of Bayesian principle has become clear to you about smoothing, and how smoothing will sort of help you to get to better solutions, and why this is a better idea to not just choose one parameter, but rather choose a distribution over parameter. And that is the key point that I was trying to get across. And now we'll try to understand how the smoothing affects the solution. Okay, so the solution will, so this kind of inductive bias that that somebody asked this question, hopefully we'll end up understanding why these solutions will be of more stable nature and better than what you get in machine learning when you use point estimation.
Hi, Andy. Sorry to interrupt. I hope
no problem.
Cut you off. So I just had one. So I mean, you already mentioned this time and again, but this came up today in the other talk as well. So basically, we can use any arbitrary loss function, regularize it with the entropy, and does that give you a Bayesian solution?
Yes.
Okay. Yeah. Okay.
Generalized Bayesian. Okay, so it's not like Bayesian. It's not Bayesian inference, but
okay.
It's a slightly bigger umbrella that I'm drawing here. It's known as generalized posteriors, and that result applies to much larger family. There have been like many papers written over the years about this, but they've been missed somehow in the Bayesian.
Sure. Yeah. Thanks.
Awesome. I think we'll not be taking any breaks today because we'll take a break maybe after 10 more minutes. So let's do this example. So let's do this example. This example is in 1.3.3 section in our paper. And hopefully the example will really clarify. So it'll be this example. I hope the fonts are big enough for you to see, but if they are not, please let me know. Put your questions here. All right, so, okay. So what we're going to do now is that we're going to try to understand this equation that I wrote in the previous slide. And I will write it with maybe green so that we understand. We're trying to see how this equation works. So basically, natural parameters are equal to the natural gradient of the expected loss. Natural parameter is equal to the natural gradient of the expected loss. And I call this like a fundamental equation. And I'm trying to kind of give you a peek on why it is fundamental. Okay. So we'll do this example, and I hope that you kind of know some details about linear regression so that I could kind of go a little bit faster and you will understand this. So if you've seen this before, you may know that the solution of this is basically, it has this form. So so the solution is X transpose X plus I inverse X transpose Y. Okay, this is called least square solution or ridge regression solution. It is available in closed form, and you can do this by just taking the gradient of the loss. So this sort of corresponds to, doing the gradient of the loss and then setting it to 0. And that will happen at this theta star. Okay, so this is, you learned this in Machine Learning 101. If you don't remember this, it's fine. You don't have to really memorize the exact form. But what is important for our purposes is that we have the solution has two parts to it. Okay, part 1 and part 2, and we'll see that these two parts correspond to the two natural parameters. Okay, so it'll turn out to be that this will be assigned to one, each individual parts will be assigned to natural parameter, and through that you can recover theta star. Okay, and that's kind of is the magic that I want to show. Okay, so the top world here, this is the machine learning world of point estimates. Okay, and the bottom world here is Bayes. Let's go to Bayes. So for Bayes, what do we need? We need to specify an approximate distribution. And of course, it sounds like magic right now, but let's just fix it to a Gaussian. Why? Well, hopefully this will be clear eventually if you read the paper. Okay, so let's choose the Gaussian. And I have said before, for Gaussian, there's a mean and the precision. So its inverse is the covariance, and S is the precision. For this, we know that there are two natural parameters. So I'm going to write them here. We have done this before. So it's S times M, and it's S in, sorry, it's not S inverse, it's half of S. And you have seen this one in the slide. I have not proved it to you, but it's basically here, it's S times M and minus S divided by 2, because you have these things appearing in front of the sufficient statistics. Okay. Now, the other thing is that mu is also, it has two parts. I'm going to just write them with mu1 and mu2. And as you remember, well, you don't have to really know these expressions, but there are two sufficient statistics. So there's two kinds of information. These are sufficient, meaning they only can be linear part and they only can be quadratic part, right? And because of this property, well, actually, if you remember from statistics, it's kind of mean and the correlation is what it is. The first one is the mean, the second one is the correlation matrix. So it's not covariance, it's the correlation. But really, you don't need to know that right now. Okay, so now we have specified all parts needed for this equation. We have lambda. Okay, we have mu, and then we have q star of theta. Okay. So we have, we q of theta. So three of those. And now what I'm going to do, I'm going to basically try to derive that equation for this example. So let's start with the, so we know that lambda star, meaning at the optimum, should be equal to gradient of mu, and it should be expectation of some q star of theta of the loss. So let's write out the loss, and loss, I'm going to put half here. And it's y minus x theta transpose, y minus x theta plus theta transpose theta, right? This makes sense. I've just put the definition of the loss. And now what I can do is I can basically simplify a little bit this loss. So I'm going to try to write this, expand this, y transpose y minus 2, 2 y transpose x theta plus theta transpose x theta plus theta transpose theta. I hope this makes sense because I've just expanded the quadratic and written it down. But now I can see that, well, this guy is just a constant, so gradient will kind of take it to 0. I don't need to worry about it. This one contains theta, and this one I could rewrite them in terms of theta transpose. Okay. So that's what I'm going to do. I'm going to redo one more manipulation, and I'm going to keep this as 2 transpose theta plus I'm going to write this as trace of x transpose x plus identity times theta theta transpose. Now, why am I doing all this? Is I hope that some of you at least can see that I'm trying to write the loss function in terms of sufficient statistics. Okay, because once I do that, now I can write the equality. I can push the expectation. So let me write gradient with respect to mu half here. And now I can push the expectation to go inside. There's a slight delay from my speaking to what happens on the screen. And maybe there's even more delay when you see it. But I hope that you are still able to follow it. So this one is mu1 and this one is mu2. Now in this case, why I chose the Gaussian, because I know that the loss is quadratic. So it can only have linear and the quadratic part. And the Gaussian is kind of have the right sufficient statistics. So that's basically what I did. And it turns out that my loss function, actually the expectation of that loss function can be written in terms of mu1 and mu2. Okay. In other words, the expectation of the loss is linear in the expectation parameter. It shouldn't be that surprising because, you know, the objective function is quadratic and the Gaussian distribution also has quadratic sufficient statistics. So it captures the form of the loss perfectly. One way to visualize this is to think that if the loss is like this, then the shape of the Gaussian is now trying to capture this exact shape. So it's trying to kind of match the mean and the variance appropriately. You're trying to put it at a place where your Q star theta, it's maybe your theta star is here, right? That's the ML solution that you'll get. But now Q star theta is trying to appropriately come to a place where the shape of the landscape and the covariance of the Gaussian kind of match with each other. So this is what I call information matching. And this is always happening whenever you're solving a machine learning method with actually stochastic gradient descent. So I hope that we'll have time to get to that. But if not, then it's, maybe I could explain that to you later on through email or some other communication. Okay, so let's finish this thing. So the last part is now to just take the gradient with respect to mu, but it's kind of straightforward, right? The gradient with respect to mu1 is going to be 2 x transpose y. I hope you can see this. And the gradient with respect to the second expectation parameter is going to be that, right? And there's a half outside, so I'm gonna now multiply the half, and sorry, there's a so multiply by half, and then I get something like this. And I also have a negative, sorry, I forgot the negative in front of the lambda star. And because of that negative, I'll just put this negative here, put the negative here. And because of that negative, this sign will change, so it'll plus, and this will be minus. So we are almost at the end now. So you see that this should be equal to lambda star. And lambda star in this case is, we're gonna now write out explicitly what okay. So now I hope you see that we have an information matching. Okay. There are two parts to the solution. Part one is assigned to the mean times the precision, and part two is assigned to the precision. Okay, so if you do the jugglery that you have to do here to say S star times M is equal to X transpose Y, then you can sort of remove S star and put it on this side. And then you know that this S star inverse is basically equal to X transpose X plus I. Okay, so what I've proved now is that theta star equals M star. And I've proved that S star is equal to the Hessian. Okay. So okay, so now I can stop here and we could discuss at this point. And my hope is that you're able to see that parts of the solution that you get in the machine learning point estimate, which is let me highlight with yellow, which is in here in this yellow part, that is somehow, assigned in here. So a Bayesian viewpoint to see this is to say that the mean and the covariance of the Gaussian are being assigned appropriately. The mean is trying to, okay, let me remove this. And I'm going to redraw the picture that I drew before. So this might be the original loss. And your Gaussian is trying to just locate itself such that the mean, so M star, is equal to theta star. So it's exactly at the minimum. Okay. And then the variance is trying to adjust to the curvature. So it's the Hessian at that point, which is X transpose X plus I. Okay. So it's really, in this simple example, you see that the information is sort of distributed. Now, the magic is, and why we are spending so much time on this, that this basically happens everywhere. Okay, so if you read this, the paper Con and Roux on Bayesian learning rule, it's essentially showing this phenomena to happen. So I have a table in the paper, and there are all of these things, and actually every single example follows the same principle. Okay, so hopefully in the rest of the talk, I can give you an idea of why that happens and again gain more insight on that, but that's where we are. So let's take maybe 6 minutes of question, then take a break for, let's say, 10 minutes, and then do the last part of the talk. Okay. Or maybe I have lost everybody here, so then there may not be any questions, and then life is easier, for me, not for you, of course. Okay, so Arun has a question. The Gaussian Q assumption is always done. No, so you can do, sorry, let me show the slides. In this table that we have in the paper here, we have a lot of examples. So there's Gaussian, then mixture of Gaussian. These are all Gaussian. So it turns out that any method that uses optimization and does like local minimum as up to second order sufficient condition, all of those methods, they're associated with Gaussian. But then fancy methods like dropout or like doing this binary neural network, these methods use variant, where you're doing mixture of Gaussian, or you're using a Bernoulli distribution, or sometimes you're using, like scale mixture of Gaussian. So they're building up on Gaussians because they're all paying attention to the gradient and the Hessian. So whenever you have a second order optimization method, it has to be associated with Gaussian, and that's the kind of is the theory here. Okay, so all methods that use second order condition can be explained with Gaussian based approximation if it's not exactly Gaussian. And then there are others that can be done with like Bernoulli and some other like Bayesian methods or approximate Bayesian inference method. They are using exponential family. So question by Pat. If I remember correctly, for ridge regression, the posterior has the Gaussian form. So in this case, is it correct to say that we are exact Bayesian because Q equals P? So excellent. So that's exactly the point here. And that's is the build-up to go to the next example. So you see here that the loss function is quadratic, and the sufficient statistics of the Gaussian is also quadratic. So the Gaussian is exactly able to match the landscape, right? So because of that, the posterior is exact. So there's no gap. But we'll see that as soon as we go to logistic regression or any other thing other than linear problem, then we'll see that this symmetric issue will not be there. And that's where things are very interesting. Why we are, when we need to get stability, our distributions have to be sort of away from bad areas. So it is connected to implicit regularization in deep learning. And unfortunately, we can't go there today, but I will explain, point to that direction a little bit. So approximate distributions will then lead to stable solutions in the sense that SGD finds stable solution, like flat minima. Okay, question by Igor. Sorry if I'm repeating someone's questions from before, no problem. But do we have to know the approximate form of the distribution Q before starting Bayesian inference? Well, it's not Bayesian inference, but before starting this principal thing that we are trying to explain machine learning, yes, we have to choose the form of the approximation. But depending on the form, you get to see different characteristics. So I will show it to you slowly that the complexity of the approximation is related to how much information you match about the loss function. In other words, here you have a Gaussian with, you have a loss function with a quadratic, and you've chosen a Gaussian with a quadratic sufficient statistics. But you could actually have chosen a smaller Gaussian which doesn't have the covariance. It has the covariance to be, let's say, fixed, and then the Gaussian will correspond to the linear sufficient statistics. And in that case, it will only capture the gradient of the loss. This will become clear, hopefully, in the next part. But there's a very beautiful property that the complexity of the approximation is related to the complexity of the loss landscape. So if you increase the sufficient statistics power, you will capture more and more information about the loss. And that's the kind of the principle that is important. And you may not kind of see it at the first time it is explained to you, but if you read the paper with this attitude, maybe you see more. Okay, what about conjugate priors, which may not always be Gaussian? Great question. So conjugate prior with non-Gaussian will exactly have the same calculation. So I think I do have a slide about this that we will not cover today because, okay. I may not have a slide, maybe. Okay, so I do I have a slide here, which is, but you can read in the paper, I think it's section 5.1 in the paper, where it is explained that when you have conjugate model, you can always write them in terms of the sufficient statistics of the distribution. So that's why it's conjugate, because Q equals, sorry about that. So Q equals P, and the loss function can be exactly written in terms of the sufficient statistics of the approximate distribution. So it always holds. So that's why all of the conjugate Bayesian inference can be actually written with the fundamental equation that that I wrote. So this equation encapsulates all of conjugate Bayesian inference and more.
So just out of curiosity, if we're not out of time, so for example, if you had to optimize something like an LDA, a lead indirectly allocation model, so how does that fit in with what you're proposing, in the sense that you use the loss function, and then add the entropy, or?
Yes, so that's basically you can recover that solution from this. Exactly is my point.
Okay.
So
fine.
yeah, what I'm saying is that the equation that's been shown here, it's kind of unifying. It unifies all the previous things that you would get. So I have it in my table. I write about this approximate Bayesian inference algorithm. So like when you do LDA, for example, it's conditionally conjugate, and conditionally conjugate methods, they are covered under this stochastic variational inference. So actually, yeah, so you can go in this section and you can read about it. So, you know, the observation, and then you have some topics, and then you have some topic proportion that are written by some Dirichlet on top. But essentially, these updates, the solution that I've talked about here is recovering the solution that people use in that literature. Okay, so there's lots of this explanation in the paper. Great. So I think we have. So let's take a break for 8 minutes again, and let's meet at 20 past whatever time zone you are at. So we'll meet in 8 minutes. Okay. So let's restart. All right, so we were doing a simple example on least squares, and we finished that, and hopefully that gives you some idea of what I'm talking about when I say that this equation that goes through the entropy is a fundamental equation. So we just did the least square case where we chose a distribution Q to be Gaussian, and the loss was quadratic, and then we see that this equation recovers the ridge regression solution. Now, this point is kind of repeated again and again in the story. So no matter what loss is, you can choose a distribution that will sort of recover the solution of the machine learning problem, but not only just the solution, but also an algorithm. So we're going to get to the algorithm part now, and then we'll understand more about how the solutions have gradient descent and the Newton method, they're related, and why this kind of Bayesian property of stability, having more stable like solutions, which, or by averaging, that kind of just appears because because of this type of behavior that goes through this equation. Okay, so before we do that, I just wanted to mention that there are some, this formulation that might seem a little bit strange to people at first if they're used to the integral formulation. So this is still P, the space of all distribution. And this was originally, it's from 1957, E.T. Jaynes, who wrote the maximum entropy principle. And it was not Bayesian at the time, but then later on, he kind of realized that this is part of a bigger thing that Gibbs originally had written, and then connected to the to Bayesian principles. So he became a really big Bayesian advocate, and he wrote a lot of papers following afterwards of why Bayes should be used most of the time in statistics. Zellner has also written about this, and this is where I learned these things. And there are lots of beautiful things in this paper and talking about how this information processing can happen sequentially. And recently, this has been again kind of brought back to statistics by Chris Holmes and colleagues. So they have a very nice paper on this. But this result actually is not, people kind of forgot in Bayesian statistics, but it is always there in the Pack Bayesian community. So it goes quite old bounced by Williamson and John Shaw Taylor, and later on by Katuni and some of my colleagues. So they're this kind of what they show is that generalization error is always bounded by objectives that look like this, that have entropy or Kale divergence built in. Okay, so it's kind of a very amazing solution, amazing field that shows that, you know, it doesn't matter if you're Bayesian or not, but if you're doing some kind of learning with a loss function, the generalization error of that will be bounded by something that depends on the entropy. So you see this formulation reappear in several places. In online learning, it has a different name. It's called exponential weight aggregate. It was originally presented, I think something that Blackwell did in, I don't remember exact year, is actually very similar to what was then later on in 90s rediscovered under this exponential aggregation. And here the idea is that there are many online learners, and then you weigh them according to a distribution or weight that is kind of exponential weight. And exponential weight is basically like a Bayesian posterior distribution. So it comes out to be a Bayesian concept. Now in neuroscience, Carl Friston has been pushing for this free energy principle, which is sometimes a little bit controversial in neuroscience, it seems like, but is also related to this formulation that I'm talking about here. Okay. Then with the approximation, so here Q is replaced, P is replaced by Q, and entropy is not there. But this kind of formulation is used in many of these. So I've just given one reference to each of this. The Gaussian homotopy is here. It's like convolving with a Gaussian. Many of these would try to include an entropy or some mechanism to keep the standard deviation not collapsing to zero. But that's kind of, or eventually it comes out to be something like having an entropy. So it's a very general concept that's related to other things. Okay, so with that, now we have around 35 minutes. So we'll just try to go through the last part and let's see how much we can cover. And materials really, like, it doesn't matter how much we cover here, but discussions are more important. So feel free to again send questions and ask them. But now we're going to try to go beyond this least square ridge regression case that we did and understand more. So far we've only been talking about the solution, but let's now write an algorithm. So usually in the machine learning or deep learning community, you'll have this kind of formulation, and then you'll write the loss. You'll optimize using a stochastic gradient, precondition gradient method of this sort, like RMS prop or Atom or your favorite optimizer from deep learning. They all take this kind of form. Now, what kind of algorithm should we use to optimize this such that we can recover this kind of deep learning algorithm and other algorithms that are used in machine learning community? So we say, well, we know that the fundamental equation is kind of saying that this should be matched with that. So I'm just going to do a error reduction. So I'm going to update the natural parameters. And I'm going to update it according to the error in the stationarity condition. One could see it like that. I hope that this makes sense. I'm actually basically just taken gradient of this with respect to mu, and I have assigned it to lambda. So I'm doing this kind of information assignment, information matching now at every step. It turns out to be a natural gradient descent or a mirror descent algorithm. A lot of this is discussed in these sections, section 2 of the paper. So there's a lot that goes on here that cannot be covered in this short presentation here. And there's a lot of beautiful theory behind it, why this is universal. But right now, what we're going to try to just quickly see is that if you change Q, the distribution Q here, you can sort of get many flavors of deep learning algorithm. Okay. And so this Bayesian learning rule, what we call, so this is Bayesian learning rule, it's kind of a superset of what we do with the gradient-based methods, for example, and many other algorithms like EM, like stochastic variational inference, Laplace approximation, and other things that are being proposed in many, many years in machine learning. Okay, so before we go there, I just wanted to give you also, I think I said this to somebody's question before, is that there's a very beautiful property here that not only by choosing Q, you can recover an algorithm. But actually, if you start with the simplest Q and then make it more complex, meaning the sufficient statistics or the shape of the distribution can be more complicated, then you'll see that the algorithm that you get out of it also becomes more complex. Okay, so the complexity of the posterior approximation is related to the complexity of the learning algorithm. Essentially, suppose that this is the true posterior, it's e to the power negative of the loss, or the exact posterior distribution, and I choose a very simplistic Gaussian approximation where I only allow the mean to change, but the standard deviation is fixed. In this case, you, as we'll see, that the Bayesian learning rule will reduce to gradient descent, meaning that if you only let the mean change, then you're getting this gradient information about the loss landscape, okay? But if I let the covariance also change, so now I don't have a circle, I have an ellipse, and I can adjust the ellipse to get, to approximate the posterior, then it turns out that the Bayesian learning rule will start asking questions about Hessian as well. So it becomes a second order method where the gradient is preconditioned by a quantity that's related to the Hessian. Okay, so this is the Newton's method. And then we can connect this to RMS prop and Adam and other things that happens in deep learning. Okay, so you see that I went from just estimating the mean to estimating the mean and covariance, and I went from gradient to Newton method, right? If you continue like this, you do like mixture of Gaussian. So now I have sufficient statistics is more rich. I can capture more fancy form of the posterior. Then we could show that it's kind of like a mixture of Newton method. It's like running parallel chains of many. It's like an ensemble method where you go to different local minima, and then you can put them together using this distribution with some proportions chosen according to the form of the distribution. Okay, if you continue like this and you let it be flexible, of course, Bayesian learning rule becomes Bayes rule. Okay, so there's a very nice one-to-one connection here. So to understand this now we have some conceptual understanding. Let's do some math. So I'm just gonna very quickly go through this example of gradient descent. So how do we recover gradient descent from Bayesian learning rule? Well, let's choose the Gaussian with a fixed covariance. So I hope you can see here that the Gaussian, it has the mean, and the mean is unknown, but the variance of the Gaussian is fixed to 1 in this case. Okay, so here this is 1, and with this, the natural parameter and the mean parameter, now they're both the expectation parameter, they're both equal to the mean of the Gaussian. There's no covariance because it's set to 1, and the entropy is constant. Okay, so it's very easy. Now I'm going to start with the Bayesian learning rule, and I will plug these definitions in, and we'll see that we'll get something that is very similar to gradient descent. Okay, so it's kind of just very simple math. Well, entropy is constant, so it just disappears. So this gradient of this term disappears, and we're just taking the gradient of this. Mu is equal to the mean. Lambda is equal to the mean, so I just get this update, right? So you see this already looks like that. Now the difference between these two updates is that here we are averaging over Q, and here we are not, okay? So if you sort of say that I don't want to sample, my jury is not going to be consisting of many, people, but only the mighty king. So I'm going to choose the mean because that's where the distribution is highest. This approximation is very well known in statistics. It's been known for centuries. It's called the delta method, where I approximate the gradient at one point. And if you do that, then you sort of get the gradient descent, right? So you have to do an approximation to the natural gradient from going from Bayesian, non-Bayesian to Bayesian, but you can always relax this and you can get something non-Bayesian, okay? And so I hope that this kind of makes sense a little bit to you of why Bayesian learning rule is kind of slightly more general than gradient descent is because here you have a mechanism to inject randomness externally. And if you want to get a non-Bayesian method out of it, you may just choose the mean. So if you start choosing the mean, then you'll get this thing. And this concept sounds sometimes very foreign to many people, but if you go to the decision, online learning community or online decision-making community, they're used to choosing the action that's kind of the most likely or the most probable action. And in that case, you can, it's quite natural to think that the gradient descent will be recovered by just using the mean in this expectation. Okay. How do these solutions differ? And I think this is where I want to spend some time, but I could take one or two questions if somebody has a question about these things, because I think people don't like this collapsing the expectations many times. So I'm happy to answer something here. Okay. Okay, so if there is no question here, then let me go back to understanding how these solutions differ and why we should not collapse the expectation. If you want to do it, you could do it and you could be completely non-Bayesian. But so if you do it, then you get the gradient descent, and gradient descent basically just looking at one point, setting the gradient to 0, and that's the solution that you get. But if you choose this solution, essentially, you can show a very nice property that your solutions, if you allow the distribution to be there, then your solutions have a slightly different, nature to them. If you apply this to ridge regression, it won't matter. But if you apply this to logistic regression, it will. So that's what I will try to explain now in the next 3 or 4 minutes. And let me go to the board here. Okay. Okay, so first order stationarity condition is that, but the Bayesian stationarity condition gives you gradient with respect to m of expectation of q star of theta of loss of theta equals 0. Okay, so you can think of the loss. So suppose that your original loss, let's use this. Suppose you have a loss function of this nature. Okay, so it's not a symmetric loss function now, like the ridge regression case, but now it's unsymmetric, meaning that, so this is like theta. And what we are saying here is that one side of the loss is more important than the other side. This is L of theta. And this could happen in cases like, you could think of like logistic regression, where you may choose like lines. So you may choose lines that are actually perfectly fine. And those lines might be somewhere going in that direction. But then if you go on the other side, so if you start to, let's say, slightly deviate from this, then you suddenly, incur like huge loss. So you're sort of going on this direction. Okay, so it's a little bit unsymmetric, the loss that your lines really kind of only can go in one direction. So other direction is very, very bad. Okay, and this type of loss function appears almost always. Okay, especially in deep learning. Okay, so suppose that the loss function has these characteristics. When you choose the stationarity condition by a non-Bayesian method, it will pick this solution. So this is very clear because it's the minimum, right? This is where the gradient of L loss goes to 0. So this is the solution by ML, right? And it's at this theta star. Now the Bayes solution, in this case, suppose that we choose the solution to be a Gaussian with only the mean being flexible. Okay, so The base solution, fortunately, well, it has a slightly different. I'm going to draw the base solution here. So this is. So theta star is here. Okay. A base solution turns out to be slightly away from theta star. So it goes in the opposite direction to where the wall is. It's because if you move slightly in this direction from theta star, you're going to suddenly make a huge mistake. And maybe if this doesn't look very good to you, you may think of this as very high wall, okay? Okay. And so it's like you have maybe a classification problem. And in this classification problem, you're at a very, very narrow place where if you have very little room to wiggle, and if you wiggle slightly, you're off. You start making mistakes of huge kind, okay? So you need to be careful about which direction you move, where you would make these changes, okay? So or you could think of it as like you're standing right next to a cliff, and if you move a little bit, you will sort of fall off the cliff and die. So you want to be careful. If you want to be careful, you will not stand right next to the cliff. You will go slightly away from it. And the base solution sort of does that. And now, how do I know that the base solution does that? The thing lies in this stationarity condition that I've written here. One way to look at this is to think of it as like you're at maybe theta star, but then you could go epsilon this side, and then you can go epsilon that side, right? And so let me draw the picture. In the picture, it will be, you'll be on here versus here. So these are two equal distance epsilon from theta star, okay? Now, if you actually start looking at the gradient of these, and I'm gonna draw the gradient. So you see here, the gradient really is high, you know? It's really saying that you should go opposite side. Don't go that side, go opposite side because I'm suffering here, okay? While on this side, the gradient is small, okay? So what the base solution will do, if the base solution is located right at theta star, if the base solution was something like this, right about theta star, it will give equal weight to both sides. Right? One gradient is really large. One gradient is small. But the distribution, I'll show it with green, it gives equal weight to both sides. Now, this is not correct because, well, it's the equation is actually saying that I should be in equilibrium, meaning that the two sides should have the same gradient for them to cancel. I hope you see that this expectation is basically trying to say that on the two sides, the gradient should get canceled. Okay. Oh my God. Okay. I'm sorry. I haven't explained one. Okay. I made a mistake. I'm sorry. Let me. This equation is actually equal to. Ooh, okay. This is an important detail that I assumed that I had given, but I had not. So essentially, there's an identity. It's in the paper that you can write the gradient with respect to m with gradient with respect to theta, okay? So essentially this stationarity condition implies that the gradient should be balanced around the mean, okay? And for that to happen, you need to put smaller weight on the, if you're in this condition, in this situation, where, let me try to draw this, that the gradient, this gradient here, is now has a very small weight, compared to the gradient here. So you can see that the distribution need to shift away from the wall to make sure that the gradient on the right side, this gradient should be weighted more. This is the intuitive explanation. You should move away from the walls where you are really incurring a lot of loss. You don't want to stay right next to it. Okay. So now I try to connect this with what happens in SGD, and you know, these things are not really kind of done understood yet in the community well, but it's quite obvious actually once you start to look into this Bayesian perspective that you could actually choose a solution with a very small standard deviation, and then you'll be there because you're not allowing much room to move. But you could then choose the standard deviation to be higher, and as you kind of do higher and higher standard deviation, your mean pushes away. Okay, so what the stationarity condition tells you is that as you are spreading the noise in your expectation, so you may actually think of it as a noise that comes from sampling mini batches, perhaps, but here the noise is coming because of an external covariance that you set a priori. In this case, you're only changing the mean. You could set the covariance to be quite large. In that case, your distribution will be very, very far from the wall. Okay. In SGD community, this is called implicit dis regularization, because what you can do is in your SGD. So let me maybe draw the SGD iterations that may actually do. So suppose SGD learning rate is set to be very, very high, then what will happen is that it will jump quite a lot, you know, and then it will jump more and more on this side. Okay, so if you actually look at the distribution of these iterates, these distributions, if you look at the marginal, it will be mostly like that. Okay, so this is kind of another way to think about it, is that the covariance that is being set by the SGD is actually kind of determined by the noise in the data. And these iterates then give you this approximate posterior distribution. Okay, so this is not kind of written with this equation, but this is known in the community. So there's papers on showing that SGD is Bayesian. It can be written as an approximate Bayesian inference, and these connections are being made. But here I've kind of explained this through this fundamental equation that I explained before. Right now, the question clearly comes out that how do you choose this covariance? And that's kind of is related to Newton method, because Newton method is kind of digging the second order information, and the second order information is somehow adjusting the scale of your gradient descent. So like maybe you're running Adam, and Adam is adjusting the scale, so Adam is giving you this covariances for free. And that's the kind of work that we did to dig out these uncertainty information from deep learning. But so we have 10 more minutes. So let me just answer this question. There's one question here, and then I'll kind of close the talk by just giving you a peek of what we have talked about and just summarizing everything. So question by Chan is, can Bayes solution be non-symmetric instead of shifting the distribution? So great question. So actually, if you don't use a Gaussian distribution that is symmetric, then you could actually have, right? So in this case, you can have a distribution. If you look at the exact posterior distribution in this case, the exact posterior distribution will be something like that, right? Because it's saying it will be heavy-tailed. It's again saying, you know why? Because it's just e to the power minus loss. This is the Bayesian principle, that you whatever is your loss, you sort of exponentiate it. You weight different theta according to this weight, and you should put less weight on the higher loss and more weight on lower loss, right? But it's very difficult to find this distribution because L of theta, the sufficient statistics of L of theta, like L of theta could be, if you write the Taylor series of it, it could be, you know, like maybe let's write it. It could have many terms, right? Sorry, I'm going to write for one dimension. Okay, so let's write another one. What Bayes is really saying is that I can stop at my sufficient statistics could include just maybe linear term, or it could also include the quadratic term. Then this is Gaussian. And I'm making a point here that all machine learning methods that rely on optimization are kind of only looking at the quadratic, you know, approximation to landscapes. So they're actually covered within Gaussian. And so they are actually assuming that the bumping is kind of symmetric. But if you start to go to dropout, if you look in the paper and we have in the table, dropout is actually doing mixture of Gaussian. So it is slightly relaxing this condition that you are sampling from a symmetric distribution, because now you're dropping the weights in the neural network, units in the neural network randomly, that somehow skews the distribution. It puts the mass away from the wall. And that's why it sort of, you know, helps in regularization. That's one hypothesis. So again, we're kind of in the beginning of, you know, writing these things down and explaining it to people. And it's not an accepted point of view, but that's why I'm here to talk to, you know, people like you. And I hope that I'm able to at least communicate the point that the Bayesian perspective of the solution helps you to understand generalization, for example, better, why these algorithms are actually doing certain things. So just to kind of close now, okay, so there's no more questions. So in the paper, there's a lot of this thing, and this kind of repeated again and again with different distribution, like mixture of Gaussian. I will encourage you to read them and see if you, you know, if you're interested and if you are convinced that this is indeed what is happening. What we actually did in the rest of the talk, what I could have gone, but you can actually find many of my talks online where I talk about this part. So it's not important that I cover everything here right now, but you can take these methods and you can sort of like the approximation that you include here, like delta method that I talked to you about for gradient descent, you can relax these approximation. And when you relax this, you can get you know, variances out of like uncertainty out of a deep learning algorithm. So that's something that's that gives you a way to improve deep learning. And again, this is like very standard math of just showing that the Newton method actually does the same thing. So you could actually write that this is Newton's method. This is derived from Bayesian learning rule through lots of manipulation, but the mechanism is the same. Then you can go and you can look into like, oh, the solution of a second order method would have positive semi-definite Hessian. Well, actually, if you look at the Bayesian solution, they're all exactly having this two condition that now the positive definiteness goes to the precision matrix of the Gaussian. So its covariance should be positive definite, and it's set to something that relates to the Hessian, right? So this has then implication in like, you know, you are trying to put your distribution somewhere where it's kind of like matching the shape of the landscape. So you will not stop at a sharp minima, but rather you'll go to a flatter minimum, right? So it's all in the equation. When you go from gradient descent type method to stochastic versions, then actually you're more into injecting noise and you're more going towards the flat things. Okay, I don't have time now, but this part of the talk you can, so we have methods that now like Adam does this kind of one line. We have a method that will look at the Adam iteration and then derive uncertainty of how much Adam moves. And the scale of that is given by the learning rate modification. And that learning rate modification can now be used to get how much perturbation we should have in doing something kind of uncertainty. This works quite well. It works for ImagiNet. So this is for ImagiNet. This was one of the first results that made it to work, a Bayesian method on ImageNet a few years ago. And it comes with a very slight modification of RMS prop. So these are kind of a modification. You can get Adam out of it as well. Implementation is available. You can do these kind of things where, you know, you do segmentation. You can look into the uncertainty of where the classifier is not very sure. Out of distribution tests. So you can do all of these things. It's all there in my tutorial, and I will encourage you to look through that. Okay, so we're almost done now. So I'm going to cover this. All of these connections, I have a new work. It's all there in the slide with my collaborators. And we are now working on new ideas on duality, where we're using the distribution in these representation to understand what a model really learns and what it should be focusing on. So you can kind of go with the distribution and you can stop certain parts of the model, and then you can see what the other parts are actually doing, which parts are important, which data examples are important. And this has been actually used to do lifelong learning. So that part, of course, I don't have, but you can check this information in the web page that's shown here. And we also have a Twitter account that you can follow. So we were very lucky. We got a lot of money for this, and we have lots of collaboration for this. It will run for 5 more projects. So this is my group. I want to thank them. They have been crucial for me to come to these ideas that I'm presenting to you today.